Hey yo, welcome to Astronaut. Today we're talking about the Bohr model of an atom, some of the equations associated with the Bohr model, and how the Bohr model is related to emission and absorption lines.
I feel like an astronaut in what you know about rolling down in the deep.
The Bohr model is a structural model of an atom that assumes electrons travel in discrete orbits around a nucleus. Take hydrogen, for example. Here we've got one proton, which makes up the nucleus, and an electron orbiting around the nucleus. For heavier elements, Bohr assumed that each orbital shell could contain a certain amount of electrons. The first shell could hold up to 2 electrons, the second could hold 8, the third could hold 18, and so on. In other words, the number of electrons per orbital shell can be found by using 2n squared, where n represents the shell number. 2 times 1 squared is 2, 2 times 2 squared is 8, 2 times 3 squared is 18, and so on. The energy of an electron in the nth shell is represented in the Bohr model by E sub n is equal to negative 13.6 eV times 1 over n squared. Where does the negative 13.6 eV come from? Well, energy is equal to the kinetic energy plus the potential energy, which by the virial theorem is just negative k. The kinetic energy is 1 over 8 pi epsilon naught times E squared over r. R, the radius of a shell, is equal to the Bohr radius, which is usually represented by an A naught, times n squared. If we substitute R into our energy equation and plug in all the constants, we get negative 13.6 eV times 1 over n squared. In the ground state, aka the lowest energy state, n is equal to 1, so the electron's energy is just negative 13.6 eV. From this energy equation, we can determine that if an electron moves from one shell to another, the change in the energy will be E high minus E low is equal to 13.6 eV times 1 over n low squared minus 1 over n high squared. When an electron drops from one shell to another, it loses energy and a photon is emitted. By contrast, for an electron to jump from a lower shell to an upper shell, the atom must absorb a photon with the exact amount of energy needed for the electron to make this transition. We give names to these emission and absorption lines. In a hydrogen atom, Lyman lines occur when an electron transitions to or from the ground state, n equals 1. An electron's transition from the ground state to a higher orbit will create absorption lines. The Balmer series corresponds to an electron's transition to or from the n equals 2 orbit. The Paschen series corresponds to a transition to or from the n equals 3 orbit. Bracket is the name we give to n equals 4, and fund corresponds with n equals 5. The names go on, but really the first 3 are the most important to remember. Let's work with an example. Using the Bohr model of a hydrogen atom, find the wavelength of a photon emitted when an electron goes from the n equals 3 shell to the ground state. So what do we know? Well, the change in energy is equal to 13.6 eV, 1 over 1 squared minus 1 over 3 squared, which equals 13.6 eV times 8 ninths, or 12.09 eV. We can relate energy to wavelength through the equation E equals hc over lambda. Solving for wavelength, we get lambda equals hc over E. If we fill in the constants and convert the energy to joules, we get 1.02 e to the negative 7th meters, or 102 nanometers. What kind of transition is this? The electron is going from a higher energy state to a lower energy state, so a photon will be emitted. That photon, of course, will have a wavelength of 102 nanometers, which is in the ultraviolet regime of the electromagnetic spectrum. Because the electron is dropping to the ground state, this transmission is part of the Lyman series. The Bohr model is far from perfect. It works well for elements with only one electron, read hydrogen and helium plus and other similar elements, but not so well for elements with more than one electron, which is most other elements. For heavier elements, experimental data differs from the theoretical predictions of spectral lines. Additionally, the model assumes electrons travel at discrete distances from the nucleus. However, according to the uncertainty principle, an electron's exact position and momentum cannot be defined, so we don't actually know if an electron is at a precise location in orbit. Well, that's all for today. We could definitely dive deeper into absorption and emission lines, so if you have a question, feel free to drop a comment. As always, ponder, wander, and go right in the stars.
Slow motion, yeah. I feel like an astronaut in the ocean. Like what you know about rolling down in the deep. When your brain goes numb, you can call that mental freeze. When the people talk too much, slow motion, yeah. I feel like an astronaut.